Hello students, this is lecture 18 of MTH 201. In the last lecture we defined vector valued functions and discussed calculus on vector valued functions such as limits, continuity, differentiability and integration. And we also defined an important notion of unit tangent vector. So this unit tangent vector is going to be used in this lecture quite often. So let us see. So we are going to talk about two important concepts today about vector valued functions. One is going to be arc length and other is going to be curvature. So first of all, we will talk about mean value theorem for a vector valued function which is going to be used when we define arc length. So let R going from closed interval AB to R3 be defined as RT equal to FT, GT, HT, and this is a vector valued function, right, on R3. We make this important assumption that the component functions f, g, h which go from closed interval AB to R are continuous on the closed interval AB and differentiable on open interval AB. Okay. Then mean value theorem says that there exists a point C between A and B such that RB minus RA is equal to B minus A, which is a scalar, times R prime C. So you can see that on the left you have a vector, on the right you have R prime C is a vector and B minus A is a scalar. So you are multiplying this vector R prime C with this scalar B minus C. And this can also be written as RB minus RA divided by B minus A is equal to R prime C. So if you remember mean value theorem from MTH 101, the geometrical significance is that when you join the line, join the points, end points of the graph of the function, there is a point in the middle such that the tangent at that point is parallel to this line joining the endpoints. And this is precisely what you have here now in terms of curves. Note that when will RB minus RA equal to B minus A times R prime C? Because RB, RA, R prime C have components. So you can, when are two vectors equal? When each of their components are equal. So this is what you will get. I'm sorry, this should be B minus A. FB minus FA is equal to B minus A F prime C. B minus GA is equal to B minus A times G prime C, and HB minus HA is equal to B minus A times H prime C. So I would like you to look at the PDF file for the correction in the last statement. Okay. So now let us define arc length. Okay. So let RT be a vector valued function on R3 with components F, G and H. You consider the curve C given by RT where T varies from A to B. Okay, so you are just looking at this vector, the image of this vector valued functions restricted to the values of T from A to B. What do we want to do? We would like to measure the length of C, which is known as arc length. Okay, so if you look at this curve C in R3, which is space, it is like a curve, right, or an arc. So we would like to measure its length. We make two important assumptions to define this concept of arc length. First is that the component functions f, g and h are C1 functions on open interval AB. What do we mean by C1 function? That their derivatives exist and they are all continuous. Okay, so they are differentiable and the derivative is continuous. Second important assumption is that this vector valued function is injective or 1, 1. Meaning that if you take two different values of t, t1 and t2 in the interval, then their image is different. Okay. So pictorially this means that the curve does not self-intersect, meaning it does not intersect with itself. And hence r prime t is a non-zero vector for all t. Okay. Next, a curve which satisfies these two assumptions is called a smooth curve. So what is a smooth curve? A curve whose all the components are C1 and it's injective. So in the PDF file, I'll add a picture of a smooth curve and a picture of a curve which is not smooth. Okay, so you can look at the PDF file for pictures. We know how to compute length of a line segment, right? It's just the, you take the difference between endpoints and take the norm, right? Now, to find the length of the curve C, what do? We will approximate C by a union of line segments. Okay, so let us see what we do. So, let us consider a partition of interval a comma b, and let me take this partition to be t naught strictly less than t1, strictly less than, and so on tk. So I'm taking k points here, k plus 1 points here, and t naught and tk are the endpoints. So in the above picture, I have divided interval AB into 8 parts. So there are 8 points, k is equal to 8. Okay. Now consider the union of line segments joining the points RTI and RTI minus 1. So now you look at the image of all these TIs on the curve. You plot them. So these dotted dots are basically image of these points on the curve. Now you join consecutive points on the curve. Okay. So when you join them, of course, here as you see between T3 and T4, RT3 and RT4, when you join them, this is the straight line, right? This is the line segment, and curve is here, right? So you can already see that when I add these lengths of these straight lines, they will not be equal to the length of this curve, right? Because you're getting something smaller in this case. So what you do is, we will see in a minute that you let these intervals, these partition become finer and finer. Okay, so you insert more and more points here, so that when you draw these line segments, they are pretty close to the original curve. So this is the same kind of thing that you have done in Riemann integration. Okay, so now the total length of these line segments is what? You add all these up, right? So the first term would be RT1 minus RT0, length of that, which is the first term here, then the second term, and so on, and you end at RTK minus 1 and RTK, right, which is RTK minus RTK minus 1, length of that. Now by mean value theorem, RTI minus RTI minus 1, because of the assumption that we have made about C1, so this difference is equal to RTI star times TI minus TI minus 1 for some TI star in this interval, right? So on each interval, you have a point Ti star, right, such that which is coming from mean value theorem. But now Ti minus Ti minus 1 is positive, so it can come out as it is, and then you have norm of this, right? So therefore the total length of these line segments is this expression on the extreme right. Okay. Now, as the maximum of this lengths go to 0, meaning this these you're adding more and more points, k goes to infinity, right? Because if this is going to 0, then you have to have a large number of uh, of points, right, in the partition. So that if this goes to 0, then the number should go to infinity, and then this above expression tends to what? It tends to the integral from a to b of norm of r prime t, right? And why is that the case? It comes from the definition of Riemann integration, right? Riemann integration, what do? You take each interval, you multiply length with the function at any point in the interval, right? So there is lower sum, upper sum, but then there is also other kind where you take any point that you wish. Okay, so from Riemann integration, this converges to this as k goes to infinity. Therefore, we define length of the curve C from a to b as this integral, and this integral exists due to assumption A on the previous slide because r prime t is continuous. So this distance is going to be continuous and therefore this integral exists. Okay. Now this is something that in this slide I'm going to make an important remark. Actually it's a result without proof. So let C be a curve which has two parameterizations, okay, R1 and R2. So for example, if you look at a circle, unit circle centered at origin, it has two parameterization. One is cos t sin t where t varies from 0 to 2 pi, and other is sin t cos t where t varies from 0 to 2 pi, right? Let's say these are the two parameterizations. Then the arc length does not depend on the parameterization. Okay, so no matter what parameterization you pick of your curve, arc length will remain same. So arc length does not depend on the parameterization of the curve. Okay, so this is, we will take it as a fact. Okay, so now that we have defined arc length, now we will define arc length function. So if you imagine that this curve is telling you how your particle is moving, so if you travel along the curve C, the arc length function St measures the length of the curve from the initial position to the position at time t, which is given by Rt. So therefore, if you take any t from A to B, St, which is the arc length function, is the integral of norm of r prime u du from A to t. So remember, when t is equal to b, then it is nothing but the arc length of C, right? So what we are doing is, we are traveling and each point we are looking at what the length is, right? So note that when t is equal to a, you are integrating from a to a, so that's 0. That's the starting point, right? There's no arc length. When your t is b, then you recover the entire length of the curve, right? And I forgot to mention here that s is an increasing function, right? Why is it an increasing function? Because you are integrating a positive function, right? So when you integrate a positive function, you have to get an increasing, you should add more and more, right? And this also comes from geometry, right? Because if you're traveling along the curve, as time progresses, you're traveling more, right? Okay. Now, using the fundamental theorem of calculus, what is S prime t? It's nothing but norm of R prime t. So, what is S prime t, by the way? It's the derivative of S with respect to t. So, that's norm of R prime t. And hence, the unit tangent vector. Now, we defined unit tangent vector in the last class. So, what is unit tangent vector? It's tt, which is nothing but r prime t, I'm sorry, this should be r prime t divided by norm of r prime t. So you normalize the vector, and r prime t is nothing but dr dt, and norm of r prime t is from the previous bullet, it's ds dt. So this becomes dr ds. So what is the tangent vector at time t? It's unit tangent vector at time t. It's nothing but the derivative of r, which is uh, the position vector, or the function that you started off with respect to arc length. This is quite important. Okay. So the unit tangent vector is nothing but the derivative of r with respect to the arc length. Now, since the norm of tt is 1, right? Because that comes from the definition of tt. It's a unit tangent vector. The norm of dr ds will also be 1 because they are both equal. What does it mean? This means that the motion along the curve is with unit speed with respect to arc length. So it may not be unit speed with respect to t variable or time, but when you differentiate, when you look at it with respect to the arc length, then it is unit speed. Okay. So this provides this motivation of parameterizing a curve by arc length instead of t, because then you are moving along it with unit speed. So physical motivation of this is the following. This is a useful way to parameterize the curve with respect to arc length. This can be thought of as placing milestones on a road to specify the location. So when we walk along the road is not straight, right? It is curved. So now after every, let's say a kilometer or 2 kilometers, there is a milestone which tells you how much distance, how much distance you have traveled till a point, or how much far ahead a location is from a point. So those are what? Those are arc lengths. They are not straight line distances, right? So therefore, it's important to parameterize your curve with respect to arc length rather than time variable. So what do we do to do this? We solve this equation. Remember ds dt from previous slide is norm of r prime t, right? So now on the left you have s as, so ds dt is, on the right you have a function of t. So what you do is you solve this equation and write t in terms of s. Okay, we'll give an example in a minute, then it will be clear. This would give us position in terms of the distance traveled, right? Now, I'm thinking of distance traveled as the arc length function, right? That's the actual distance you're traveling along the curve. Just write reading on the milestone, how much you have covered. Let us look at this example. So consider this curve RT in R3, which is cos t sin t, where t varies from 0 to pi. Then r prime t is what? You differentiate each component, you get minus sin t cos t1. Therefore, if you look at its norm, it comes out to be square root 2, right? Which is square of sin t plus square of cosine t plus square of 1, which gives you, and square root of that, which is square root 2. So by definition, what is st? It's integral 0 to t, 0 because that's the left hand point, time 0 to t integral of r prime u norm, which is square root 2 du, which comes out to be square root 2 t. Now this is the arc length function, right? Now what is the length of the curve? Length of the curve we know is s at the value pi, right? That's the total length, which comes out to be square root 2 pi. So that's the length of the curve C. Now if you express t in terms of s, now from this expression you see s is equal to square root 2t, right? So from here t comes out to be s by square root t, right? So now you consider this new parameterization of C. Now not with respect to t, that's given to you. Now with respect to s, which is the arc length. So what is r tilde s? R tilde s is nothing but R of Ts. So what you are doing is now you are replacing the variable t by s. So R of Ts, but Ts is equal to s by square root 2, right? T as a function of s is s by square root 2. Now what is R of s by square root 2? Now you replace here t by s by square root 2. This is what you get. But then what are the possible values of s? S goes from, now what are the possible values of s? Now it goes from, so what are the possible values of t? It's 0 to pi, right? That means the possible values of s will be s of 0 to s of pi, which is 0 to square root 2 pi, right? Now if you differentiate r tilde with respect to s, this is what you get by chain rule. Now this is a unit vector, right? This is very important conclusion, that when you differentiate, when you look at the curve now with respect to arc length and you differentiate at any point, it becomes a unit vector. So now the unit tangent vector, the tangent vector with, when you have parameterized your curve with respect to arc length, is a unit vector. It's very crucial. So the tangent vector t tilde s, which is r tilde prime s, right? Which is what? What is r tilde s? It's r of ts. So when you use chain rule here, you get r prime of ts times t prime s, right? Which is dt by ds. Now what is r prime ts? It's nothing but r prime t. You can think of it as r prime t. And dt by ds is the reciprocal of ds by dt. But ds by dt is nothing but norm of r prime t, right? By from the arc length function definition. So therefore, if you look at the norm of t tilde s, it's nothing but 1, right? Because norm of this is 1. This is already a unit vector, right? So norm of t tilde s is 1 for all s. Therefore, when parameterized by the arc length, at each point along the curve, the tangent vector is a unit vector, right? Okay. So let me go back. So if you would like to pause, I would advise that, I would encourage that at this point, because this lecture is quite dense, and we are going to move to the concept of curvature in the next slide, in the next few slides. So you can take a break now and come back and then look at the remainder of the video. Okay. So let us define curvature. So the first few slides are going to be motivational slides. So the curvature of a curve measures how fast the curve bends or changes its direction at a given point. So if you look at this picture here on this slide, this curve is the curve that is in consideration. So I've taken 3 base points and I have drawn these circles here, right? What are these circles? They are circles which best approximate your curve at that point. Okay, so I have sort of inscribed circles here as big circles as possible, which can be inscribed. So here you can see this is the circle that can be inscribed. Here this can be inscribed. This is a very rough picture. So I am not saying that you can't do more, but roughly let's say this is the best you can do, and here you have this. So if you look at this middle one, you curve very fast or you bend very fast on this curve, right? So there is more bending. And more bending means high curvature because you're bending more. Curvature is the measure of how much you're bending. So if you're bending more, you will have higher curvature. While on the other two, you bend slow, right? You bend slowly. So you have less bending and therefore you have low curvature. Okay, so pictorially this, you can keep this picture in mind to understand what curvature is, right? So let us look at two examples. If you look at a straight line that does not bend at all, right? And hence it should have zero curvature at every point because there is no bending. If you take a circle, the bending of a circle is the same at every point, right? You bend equally along the circle at every point, and hence the curvature should be constant at every point. We will come to this example later. But roughly now you have kind of a sense of what curvature is. So intuitively, the curvature is the rate at which the angle of the tangent vector changes as we move along the curve. On a road, the speed limit is lowered on a curve on a road, right? So when you walk along or drive along the curve on a road, you slower your speed, right? Because the curvature is higher, right? And you don't want to meet with an accident. So you lower your speed when you hit a curve, right? Okay. Thus, the rate of change of angle of the tangent vector will depend on the parametrization of the curve, right? To eliminate this dependence on the parametrization, we work with the arc length parametrization, which we defined just now, which means that we move along the curve with unit speed. So let us see what I mean by this. So I'm going to motivate you with what happens in R2. So let me show you this. So using the arc length parameterization R tilde s which we defined, the unit tangent vector uh, T tilde s is nothing but R tilde prime s, right? It's already unit. Its norm is 1, right? So if psi s denotes the angle of the tangent vector T tilde s, so you have this curve which is parameterized now with respect to the arc length, which is s. So this point is, let's say, r tilde s, and you look at the tangent vector, right, which is t tilde s, which you know is a unit vector. Suppose it makes the angle psi s with positive x-axis. So then this t tilde s can be written as cosine psi s sine psi s, right? Because it's a unit vector. So if you differentiate this vector with respect to s, use chain rule, you get minus psi prime s sine psi s, comma, psi prime s cos psi s, right? Which implies that when you take the norm of this comes out to be mod of psi prime s, right? Which is nothing but square root of sum of squares of these two terms. So this means that when you differentiate t tilde with respect to s and take its norm, it's nothing but the, there should be norm here, double bars here. This is nothing but the absolute value of the derivative of psi, which is how the angle is changing, right? And this gives us inspiration to give the definition of curvature. So the curvature, which is a function of t. So this is the symbol that's used for curvature. This is called kappa. So kappa t of a curve is given by, which is curve which is given by this is defined as the magnitude of the rate of change of the unit tangent vector with respect to the arc length, st. So kappa t is nothing but norm of dt ds. Okay, so you differentiate t now with respect to s. Now with respect to s, you know that in the parameterization you have nothing but the unit. The tangent vector is a unit vector, right? So this is the definition of curvature, right? It's a norm of the derivative of the tangent vector, unit tangent vector with respect to s. So you notice here that I have not used the tilde notation at all because it's not required. What you get in the end is basically you don't have to define new parameterization and so on. You just get this formula from the previous discussion. Now notice that if you look at t prime t norm, that's norm of dt dt. Now this can be written as norm of dt ds times norm of ds dt. But norm of dt ds is kappa t by definition, and norm of ds dt is nothing but norm of r prime t by definition of s. Therefore, kappa t is nothing but norm of t prime t divided by norm of r prime t. Okay, so this is another formula for kappa t, which is more useful, right? Because now there is no dependence on arc length function. This formula now is completely independent of arc length. Okay. The vectors tt and t prime t are orthogonal. Why? Because norm of tt is 1 for all t, right? It's a unit tangent vector. So if you take square on both sides, you get 1 equal to norm tt square. But norm tt square is the dot product of tt with itself. You differentiate with respect to t, the left hand side gets 0. Right hand side you use chain rule, product rule, and you differentiate, you get twice of tt dot t prime t, right? So therefore tt dot t prime t is 0 and therefore they are orthogonal vectors. You have another formula for curvature in terms of position vector and its derivatives, and this is the formula which we will now prove. So tt is equal to r prime t by norm of r prime t, right? By definition. And norm of r prime t is ds dt. So therefore putting these two things together, r prime t becomes ds dt times tt, right? Now you differentiate this equation that you have with respect to t. On the left you get r double prime t. On the right you get d2s dt2 tt plus ds dt t prime t. So if you take cross product, which is the numerator here, the cross product of r prime t with r double prime t, you are taking cross product of this term with this term. Then this becomes, so you see you can distribute it, right? This is first ds dt tt cross with d2s dt2 tt plus the second term. But if you take the first term, that will give you no contribution because tt cross with tt is 0. So therefore you get only the second term, which is ds dt tt times ds dt t prime t, which becomes ds dt square tt cross t prime t. Therefore norm of this is nothing but this square norm of t prime t. Why? Because they are orthogonal, right? So by the parallelogram law that we saw, we have norm of this cross product is nothing but product of norms of individual vectors, but tt is unit vector, so you only get this term, right? But what is ds dt? ds dt by definition is norm of r prime t, and you have a square, so this is what you get. So therefore kappa t by definition from the previous slide was norm of t prime t by r prime t. But norm of t prime t now is nothing but this norm divided by square of this term, and then there's an extra term, so this is what you get. You can pause for a minute, and these are straightforward computations. You can just verify them. So let us look at two examples where we will compute kappa t or the curvature. So consider this function r cos t, r sin t. This is the graph. This is the parameterization of a circle of radius capital R in R2 centered at origin. R prime t you can compute, R double prime you can compute the norm of R prime t. From the formula on the previous slide, we need this cross product, which comes out to be this, and therefore norm of this comes out to be r square. Substituting in the formula for curvature, you get r square by r cube, which is 1 by r. So if you have a radius, circle of radius r, capital R, then its curvature is its reciprocal. So now things match together, right? If your radius is really large, so since the circle bends or curves in the similar way at all the points, the curvature is a constant function. It doesn't depend on t. Moreover, as the radius of the circle becomes larger and larger, there is less bending, and therefore curvature becomes smaller and smaller. So as r becomes really large, kappa becomes really small. Another example is that of a helix, and we already saw this example when we were describing arc length parameterization. So consider RT to be cos t sin t. So if you look at this one, let's say this is the x coordinate, this is the y coordinate, this is the z coordinate. There is a very nice relationship, which is x square plus y square is 1, right? Therefore, when you look at the graph of this function, it lies on the cylinder x square plus y square plus equal to 1, and this is the image. Okay, and this graph is known as a helix. You can easily compute r prime t, r double prime t, compute the norm of r prime t, take the cross product, compute the norm of that. Substituting in the expression for curvature, you get, this is the formula, you get 1 by 2. Again in this case, you have constant curvature. So again in this particular case, your curve is bending similarly in all along the, you're bending in the same way along the curve. Okay, so it's not apparent, but it comes out to be like that. Okay, so let us stop here. So there are going to be a few corrections in the PDF file, so you can also watch out for those corrections. They will be marked in blue color. Okay, so let us stop.